Hello everyone, we are in our one-dimensional kinematics notes. We are going to look at example number 3 in the horizontal direction. So go ahead and turn to page 8 where example 3 is located. Alright, so we're back. We are going to take a look at this example. It's having a driver having to make an emergency stop while driving a vehicle. There's a certain amount of time that elapses until the brakes of the car are actually applied. The time that elapses is commonly referred to as the driver's reaction time. Now let's suppose this driver is driving her car at 28 meters per second and a cat runs out in front of the car. Let's also suppose that her reaction time is 0.5 seconds. When she applies the brakes of her car, it decelerates at 6 meters per second squared. And we want to know how far will the car travel from the time the driver sees the cat until she stops. So go ahead and take this situation, take the words and convert it into a picture here. Pick up with me once you've stopped the video and drawn your picture. All right, so here we are. This is the picture I have drawn. And you'll notice that this is slightly different than some of the other examples we've looked at. You notice here that there's a section. I've split it up into two parts. Now I'd like you to think about why have I done that? And ultimately what it comes down to is that when we apply the kinematics equations, the kinematics equations are good only for constant acceleration. Now the problem with this problem is that we have two parts to it. The parts meaning different accelerations. The first part of this is where we have some reaction time happening. There's a half a second, I believe it was, that elapses between when she sees the cat. Okay, so the seeing of the cat happens right here. Before that happens until she hits her brakes. So right here she's actually applying her brakes. So during this time we're going to kind of make the assumption that the car is traveling at for the most part, a constant speed. Now, of course, we could get really technical here and say that when she lets up on the gas pedal, it slows down slightly, but we'll pretend the cruise control's on. After she applies the brakes, of course, we have a deceleration happening. And so since we have a deceleration happening, our acceleration is going to be in the opposite direction of our motion. And again, think about this from the standpoint of a force. A force would cause, you'd have to push in the car in the opposite direction to make it actually slow down. So that's why our acceleration is here in this direction. Now ultimately we want to see, or we hope that she stops here to save this poor cat that got loose. So we're going to hope that it does stop, or we're going to say that it is going to stop here eventually. So ultimately here, we are trying to find this total distance, and my knowns and find are here. And again, because I have two parts to this, I've kind of separated my knowns into two sections. The known section for part 1 and the known section for part 2. I've taken into account, and this one's going to be kind of really important that you do take into account the directions. I haven't been too worried about that before, but because I'm definitely dealing with positives and negatives here, I definitely need to worry about that. So I am going to attempt to find the distance first that she travels while reaching for her brake, and I'm going to find the delta x part here as well. So I'd like you to go ahead and stop the video. Think about what equation or equations you would need to solve for this problem. All right, so here we're back. We are in part 1. Let's take a look at the equation I picked here. I just picked my speed equation. The speed equals distance over time. Since we're dealing with a constant speed here, this equation works just fine. So what you're seeing here, I'm just showing you how I solve for isolate the d. And again, I just need to multiply by the t on both sides. So just doing some algebra. So of course, this is now ready to put my numbers in. We'll do that in the next part, in the solution part. Over here, part 2 is where we actually have the deceleration happening. And since we know nothing about the time in this one, okay, now you got to remember the time that we know happens in that between these first two snapshots. So the time is not occurring over here. So again, this is something you need to watch out for. And I don't even have my time written here, but if I was to put it in, my time would be from this snapshot to that snapshot. So we don't actually know time here. So you need to be careful. Just again, don't just pick numbers and say, oh, well, I know time. Let's pick an equation with time in it. You gotta really think about what you're doing. So I've simplified here a little bit, and my final velocity is 0. So I canceled that out. I'm just going to try to isolate the delta x, the displacement. And after doing so, let me just slide this up just a little bit. After doing so, I end up with actually a delta x equaling a negative VO squared, or V sub O squared, over 2a, or negative 2a. Now, of course, you should know here, of course, these negatives cancel out. We are now ready to put some numbers in. Although I guess before we really do that, we always should check our units. And of course, they do work out in this case. And again, here's my work for that. Let's go over and put the numbers in and see what we end up with. All right, so here we are back with the numbers. And again, one thing you want to be careful of here is making sure that you're putting the right numbers in the right places. So again, that's why I separated my knowns into two sections. So this is part one, and I've only used the numbers in here that go in part one, and then down here I've again substituted the numbers that go in for part two. So ultimately, again, because there's this travel time while she's reaching for her brakes, and then there's this travel time while she's actually decelerating or slowing down, we have to take the total of these two to actually figure out how far she is moving while doing the slowing down to a stop. Ends up being 79.3 meters. Now, one thing I'd like to do with this one is we're going to go back here. Let me just grab this right there. And we also can take, we've looked at the words of this problem. We've looked at the pictures of this problem. We've looked at the equations of this problem. Okay, these equations are what kind of drive, and no pun intended there, I guess, but these drive how we solve this problem. We're now going to look at, I want you to think about how the graphs, or what the graphs would look like for this if we were to draw, let's say, a distance versus time and a velocity versus time. So let's have you go ahead, stop and think, draw a distance versus time and a velocity versus time graph for this particular problem. All right, so here we are. We're going to try to make a graph for this. And so I've done a really rough sketch of this situation again down here. And let's take a look at our distance versus time graph first. So between this one and this one, again, we're told that there's no acceleration, so I could say the acceleration is 0 here. So we know on a distance versus time graph that an acceleration of 0 means that we have to have a straight line. And since we know it's moving at a certain speed, it has to be a slope here, and it's going to look kind of like this. Next part of it is that we want to have a negative acceleration. We also know that it has to be slowing down. It has to be decreasing its speed to a 0. So from this point forward, it's going to have to change how it's moving. So we're going to have a slope down kind of like this eventually until it reaches a flat line. And if you think about the slope here, the slope is getting smaller, it's getting smaller, it's getting smaller. Slope, remember, is the speed or the velocity, I guess I should say, is more specific or more correct. Now, let's go over and take a look at our velocity versus time graph. Now, of course, we could talk about these being speeds, and the only difference really between speed and velocity is that we're giving it a direction. So because we drew this speed as a vector, it has a direction, and therefore a speed is a velocity. So we have our car. It has, based on our positive direction here, it actually has a negative velocity to start. Now that's going to be a problem here because this is our axis is the wrong way. So let's just, let's pretend this doesn't exist down here, and let's put our axis right there. So we have our positive velocities up here and our negative velocities down here. So again, let's just get rid of this guy right there. Now, since it's a constant velocity, some of us might say, well, oh, it's got to look like this. There's a constant velocity. Well, you got to remember, that's a certain velocity here, and there's a different velocity. So the velocity here is a constant velocity, constant, and it's trying to show that that's a horizontal line there. Again, so constant, it's at any time, it's the same value, whatever this value is over here. Well, it was 28 meters per second, I guess, wasn't it? At that 0.5 seconds, which would be right here, likewise on our distance graph right there, we begin to decrease, okay? We begin to decrease our speed, and so our car eventually stops. And apparently when cars stop, they become flat like a pancake. But anyways, we do have our acceleration. Notice again, the acceleration is in the positive direction. And we have to be going down here to, we reach a velocity of 0. Right there's our velocity of 0. And again, notice the slope of this. Slope on a velocity versus time graph. Slope is equal to the acceleration. That was a poor attempt at acceleration, but there we go. Acceleration, since slope is acceleration and slope is positive, therefore our acceleration is positive as well. So our two graphs would look like this.